We are going to be looking at problem 8.37, which is a convection problem. So looking at the problem, it says we have a 50 millimeter thin-walled tube that is maintained at 100 degrees Celsius. And in one case, air is in crossflow over the tube with a temperature of 25 degrees C and a velocity of 30 meters per second. And in a second case, the air is in fully developed flow through the tube, also with a temperature of 25 degrees C and a velocity of 30 meters per second. And it asks us to compare the heat flux from the tube to the air in both of these cases. So the big thing about this problem is that we have two cases, one here in crossflow and another here in flow through the tube. So we have one case of external convection and one of internal convection. So we're going to start by drawing two separate schematics, one for each case, and also writing down all of the given information for each one. I have drawn a couple schematics here. The first one for case 1, we see external flow. In case 2, we see internal flow. All of the properties are the same of the tube, the temperature and diameter are the same, as well as the velocity and temperature of the air. I've written down a couple material properties, viscosity, thermal conductivity of the air, and the Prandtl number. The next thing that we have to do is just identify what they want us to find, which is just the convective heat flux for each of the two cases, and then also identify some important assumptions, which are just going to be steady state, uniform surface temperature, as well as for the internal convection, specifically fully developed flow, and the air is an ideal gas. So it's time to now go ahead and actually solve the problem now that we've got everything written out. And we're going to start with case 1. So as with any convection problem, the first step is to find our Reynolds number, which we calculated as 7.69 times 10 to the 4th, which for external flow is laminar. And because we are working with a cylinder here, we know that the equation that we need for Nusselt number is this fun guy right here. So we're going to go ahead and plug in Reynolds number and Prandtl number into that, and that will find our Nusselt number. So with all the values plugged into our big equation, we get this, which once you spend a bunch of time typing that into your calculator, you get a Nusselt number of 180. And of course, this is unitless. So the next step is to find our H value, which we can just use the much more friendly K over D times the Nusselt number. So plugging in the K value of the air, the diameter of the pipe, and that Nusselt number we just calculated, we get a convection coefficient of 104 watts per meter squared Kelvin. And then from here, we just need to find heat flux, which we can do with the simple equation H times delta T from the first chapter. And we are finding heat flux, so there's no need to worry about areas. And after just a little multiplication, we have our heat flux for case 1 of 7,840 watts per meter squared. So we can go ahead and move on to case 2, which is internal convection, but with the same properties. Starting off case 2, we get a little shortcut here because we had the same velocity and diameter and viscosity of the air in the tube. And so we know that we will have the same Reynolds number. The difference is that because this is internal flow, the kind of transition Reynolds number is around 2300, which means that we are in the turbulent region for case 2, which that combined with our assumption of fully developed flow gives us this much nicer equation for Nusselt number. So we'll go ahead and plug those values in. The Prandtl number is the same because it's the same air, and we will find a Nusselt number. So plugging those values in, we get a Nusselt number of 162, again unitless, and just like before, we are going to use K over D times the Nusselt number to calculate our convection coefficient. So I went ahead and calculated our H, which is 94 watts per meter squared Kelvin. And then because it's essentially the same thing we did before, I went ahead and calculated our heat flux as well using the H delta T equation. And I got for the internal convection case 2, 7,040 watts per meter squared. And quickly to wrap up here, just a couple of conclusions. Comparing these two values, they are pretty similar, only off by about 10%. Yeah, they are pretty similar. The air in both cases was pretty similar as far as temperature and velocity goes. We can also notice that the solution methods for the internal and external cases were basically identical. Find a Reynolds number, pick an equation for Nusselt number, calculate that Nusselt number, calculate convection coefficient, and then heat flux, which, looking back at case 1, is essentially the same thing. Reynolds number, pick an equation, Nusselt number, convection coefficient, and heat flux. This is pretty much the same process for any convection problem.